Hello everyone and welcome to this Kubernetes networking tutorial. In this video, we are going to build a public website running on Kubernetes. And more importantly, we will understand how traffic from the internet reaches application running inside a Kubernetes cluster. When developers first start using Kubernetes, they often encounter a common challenge. The application runs perfectly inside the cluster, the pods are healthy, and the services are working internally. However, when they try to access the application from a browser, it simply does not work. Why? Because Kubernetes by design does not export application to the public internet automatically. This is actually a very important security feature. So the key question becomes, how do they safely export application running inside Kubernetes to external users? In this project, we will exploit the solution using NGINX Ingress Controller and the Kubernetes networking object called Kubernetes Ingress. By the end of this tutorial, we will understand how traffic flows from the internet into Kubernetes, how to route traffic to different services, how to organize a clean microservice architecture, and how to manage external assets in a scalable way. Let's start by understanding the core problem. Exposing application. Because we talk about solution, we first need to understand the problem. Inside Kubernetes, applications typically run in pods. Pods are the smallest deployable unit in Kubernetes, and they contain containers running our application code. However, pods are ephemeral. They can be recreated at any time. Because of that, Kubernetes introduces another object called a service. A service provides a stable network endpoint that routes traffic to pod. But by default, most services use a type called cluster IP. Cluster IP means that the service is only accessible inside the Kubernetes cluster. So the architecture looks like this: pods to service. This works perfectly for internal communication between services, but it creates several problems. First, users on the internet could not access the application. Second, there is no public entry point to the system. And third, if we have a multiple service, there is no easy way to route requests based on URLs or domain. Imagine running a real website with multiple APIs, microservices, and front-end application without a proper external gateway. Managing traffic would become extremely difficult. So we need a clean and scalable way to expose services to the outside world, and that is where Ingress comes in. Solution Ingress. To solve this problem, Kubernetes introduced a powerful concept called Ingress. Ingress acts as the main entry point for external traffic. You can think of it as a smart traffic router sitting at the edge of the cluster. Instead of exposing every service individually, we create a single entry point that receives all external requests. The architecture becomes Internet to Ingress Controller to service to pods. The Ingress Controller functions very much like a reverse proxy. It inspects incoming requests and decides where to send them based on rules we define. Ingress provides several important capabilities. First, it allows HTTP routing, meaning different URLs can go to different services. Second, it supports domain-based routing, which is essential when hosting multiple websites. Third, it can perform SSL termination, allowing HTTPS encryption. And finally, it provides load balancing across ports automatically. In production environments, many organizations use Ingress controllers such as NGINX Ingress Controller, which is one of the more popular implementations. In this project, we will use NGINX Ingress to expose our application. Project architecture. Now let's look at the architecture of the project we will build. Our system contains two microservices. The first service is the Frontend, which provides the user interface of the website. The second service is the Backend API, which contains the business logic and return data. Both services run inside Kubernetes as a deployment and box. However, instead of exposing them directly, we replace an NGINX Ingress Controller in front of them. The Ingress Controller receives on external traffic from the internet and routes it based on URL path. This means that when a user opens the website homepage, the request goes to the front-end service, but the controller calls the API. The request is routed through the backend service. This pattern is extremely common in modern microservice architecture. It allows different services to remain independent while still appearing as a single unified application to user. Architecture diagram. Let's visualize the architecture more clearly. At the very top, we have user accessing the website through a domain name demo.local. Their requests travel across the internet and arrive at the inquiry controller. The inquiry controller then evaluates the routing rules and decide which service should receive the request. If the request targets the main website, it goes to the front service. If the request targets an API endpoint, it goes to the backend service. Each service then forwards the request to the appropriate pods running the application containers. This layer architecture provides several benefits. It improves scalability because we can scale pods independently. It improves flexibility because we can easily add new services, and it improves security because the Ingress acts as a control gateway into the cluster. Service in the project. Now let's take a closer look at the two services in this project. The front-end service is responsible for the user interface. It displays the website and interacts with the user through the browser. Whenever the front-end needs data, it sends requests through the backend API. The backend service, on the other hand, handles application logic. It processes requests, interact with a database, and return structured data often in JSON format. Data separation between front-end and backend is a very common design pattern in modern applications. It allows front-end developers and backend developers to work independently, and when combined with Kubernetes, it becomes very easy to scale its services depending on traffic demand. Kubernetes object use. To build this system, we rely on three core Kubernetes objects. The first object is a deployment. A deployment manages box and ensures the correct number of replicas are always running. It also enables rolling update when we deploy new version of the application. The second object is a service. A service provides a stable internal endpoint and load balancer traffic across POP. Without services, communication between POP would be extremely unstable. The third object is Ingress. Ingress defines rules for how external traffic enters the cluster. Together, these three objects form the foundation of many Kubernetes applications. Traffic flow. Now let's talk through the complete traffic flow of a request. Imagine a user open the following URL, demo.local data /API/users. The request beginning in the user browser is travel across the internet and arrival at the Kubernetes cluster Ingress Controller. The ingressor inspects the request path because the path begins with the /API. The ingress forwards the request to the backend service. The backend service then load balances the request across backend POP. Finally, the selected POP processes the request and returns a response. The response is traveled back through the same path, eventually reaching the user's browser. This entire process happens in milliseconds. Deployment step. Deploying the application is surprisingly simple thanks to Kubernetes declarative configuration. We define owner infrastructure using YAML files. The deployment process follows 5 steps. First, we create a namespace to isolate our resources. Second, we deploy the backend service. Third, we deploy the front-end application. Fourth, we create the services that expose the pods internally. Finally, we configure the ingress rules that expose the application externally. Other bits can be executed using simple kubectl apply command. This is one of the reasons Kubernetes is so powerful. Infrastructure become code. Domain routing. One of the most powerful features of Ingress is path-based routing. Instead of running separate load balancer for each service, we can route requests based on URL paths. This allows multiple services to share the same domain name. It also creates a much cleaner architecture for APIs and web applications. As a system grows later, this type of routing becomes essential. SSL and HTTPS. Another important capability of Ingress is TSL termination. This means the Ingress controller can handle HTTPS encryption. Incoming HTTPS traffic is decrypted at the Ingress layer and then forwarded internally using HTTP. This simplifies certificate management because SSL certificates are handled in a single place. It is into performance and security. In production environment, Ingress is often integrated with tools like Cert Manager to automatically generate and renew TSL certificate. What we learn after completing this project, we now understand how Kubernetes networking works in real-world application. We explore how services enable internal communication. We learn how Ingress exposes application to external users, and we saw how routing rules allow multiple services to operate under a single domain. These concepts are fundamental when building scalable microservice platform on Kubernetes. Now review this flow project. Demo up. When we run applications inside a Kubernetes cluster, they usually run inside pods and are exposed through services. However, most services are only accessible inside the cluster. This means users on the internet cannot directly access our application. To allow external users to reach our service, we need a component that can receive traffic from the internet and route it into the correct service inside the cluster. This is where the NGINX Ingress Controller comes in. The NGINX Ingress Controller acts like a smart gateway or reverse proxy for the Kubernetes cluster. All incoming traffic first arrive at the Ingress Controller. It then tracks the routing rules and forward the request to the appropriate service. For example, traffic going to Slack can be routed to a front-end service, when a request to Slack API can be routed to a Backend API service. Installing an Ingress controller provides several important benefits. It allows multiple services to share the same domain, support path-based routing, enable HTTPS or SSL termination, and simplify the overall network architecture. In short, installing the NGINX Ingress Controller is essential because it provides a single, flexible, and scalable endpoint for external traffic into a Kubernetes cluster. This YAML file defines an ingress resource in Kubernetes. An ingress is used to route the external traffic from the internet to service inside the cluster. In this configuration, the resource uses Kubernetes ingress and is handled by the NGINX Ingress Controller, which is specified by ingress class name NGINX. The ingress is named public ingress and it belongs to the public web namespace. This means it manages routing for applications running in that namespace. Next, we define a rule for the domain demo.local. When a user opens this domain in a browser, the request will first reach the ingress controller. The ingress then checks the URL path and decides which service should handle the request. If the request path is slash, the traffic is routed to the front-end service on port 80. This service typically serves the website interface. If the request path starts with /API, the request is routed to the backend service on port 80, which usually handles API requests. So in summary, this ingress configuration allows one domain name to route traffic to multi-services based on the URL path, which is a common pattern when building microservice application on Kubernetes. When we run Kubernetes locally using Minikube, our application runs inside a local Kubernetes cluster. However, some Kubernetes services, especially those with the tight load balancer, normally require a cloud provider to assign a public API address. In cloud environment like AWS or Google Cloud, the platform automatically creates a load balancer and gives the service an external API. But when we run Kubernetes locally with Minikube, there is no cloud load balancer available. This means the service will stay in a pending external API state. The user cannot access it from outside the cluster. To solve this problem, we run the command minikube tunnel. This command creates a network tunnel between your local machine and the Kubernetes cluster. It simulates on cloud load balancer and assigns an external IP address to service that needs one. As a result, external traffic from your browser can reach the service inside the cluster. In short, running Minikube tunnel allows local Kubernetes services, especially load balancer services used by tools like the NGINX Ingress Controller, to be accessed from outside the cluster, making it possible to test real-world networking behavior on your local machine.